In this session, Predict the Future, or Don't, with machine learning in applications, we'll look at the ease with which you can build models and make predictions using Oracle Machine Learning through the Oracle Database Platform. After a brief introduction, we'll demonstrate building models and making predictions in the database. I'm Mark Hornick with Oracle Machine Learning Product Management. Thanks for joining me. Many have commented on the challenges of prediction, whether regarding world dynamics, sporting events, or the stock market. When it comes to predicting what will happen, we typically draw on three approaches. Intuition, a go-with-your-gut approach to decision-making, where individual biases can cloud or at least influence predictions. Then there are statistics, where we gain evidence to support a conclusion. And then there's machine learning, where we use advanced algorithms to understand patterns in past data, make predictions, and glean insights. Now, with respect to machine learning, use cases include, for example, predicting customer behavior, such as buying a product, dropping a service, or becoming a new customer. There's predicting product failures, such as how soon a product is likely to fail and why. Identifying potential insurance fraud. Is a given claim unusual enough to warrant further investigation, just to name a few. Now, we can also use machine learning to segment customers, to understand the factors that most contribute to a customer's lifetime value, or a patient's likelihood to benefit from a medical procedure. In its simplest terms, we have data and machine learning algorithms, and these produce machine learning models. A model contains the patterns found by the algorithm in the data. And these patterns are then used to make predictions or better understand the data. Of course, data often needs to be transformed to meet both the needs of the business problem as well as the algorithm. And during the modeling process, algorithms have settings that affect model quality. Some algorithms automate tuning such settings, or users can adjust them manually. Then we evaluate model quality, possibly going back to change algorithm settings, transformations, or to include other data sources. Perhaps we do all three. Once we have a model, we can use it to make predictions, or what we also refer to as scoring or inferencing. These predictions can be on a single record or an entire table with data on millions of customers. Of course, the story doesn't end there. These predictions often provide the most value when consumed by application users. Now, the other side of the coin, the or don't part of this session's title, is gaining insights using model details. That is, the patterns themselves that the algorithm discovered and stored in the model. These can be in the form of rules, whether from a decision tree or market basket analysis. Or perhaps we want to understand the relative importance of data provided to build the model. This can be in the form of coefficients or an importance ranking for each data column. There are also a variety of model metrics we can inspect to understand model quality. Let's drop down a level and look at some sample data that could be used by machine learning algorithms. Most enterprises have data about their customers and their purchases. Here's a simple example that could support predicting if a customer will buy a given product. Of course, this product could be anything, a physical object, a service, or a movie to watch. Customer demographic data and purchase behavior could be all you need to build a model to predict if new customers for which we have similar data are likely to purchase and with what probability. Automation can also play a role in helping to produce models. AutoML can streamline aspects of the machine learning process, eliminating the manual tasks of exploring multiple algorithms and their settings to produce better models. As such, AutoML aids data scientists as a productivity tool, but it also enables non-experts who might not be familiar with each algorithm's data preparation requirements or settings. Of course, AutoML also has its limitations. Like machine learning in general, the adage holds, garbage in, garbage out. The data needs to support the use case, have reasonable quality, and be properly transformed. Also, AutoML doesn't replace the need to clearly define business objectives or to have a reasonable target to predict. So let's first see a demonstration of the AutoML user interface, a no-code interface that automates model building for in-database algorithms. Then we'll look at the SQL and Python interfaces for building models in the database. Let's see a demonstration of the AutoML user interface. We'll start by creating a new experiment. And we'll give it the name Product Purchase 2. We'll choose our data source. We'll search for OML user schema and the customers table. What we want to predict is the target purchased, whether or not the customer purchased the product. And we specify the customer ID as our unique case ID. Let's look at the predictors. These are also referred to as features, and these are the ones available in our dataset, with table statistics such as the number of distinct values, among others. Users can deselect features to exclude them when building a model. There are optional settings such as how many tuned models the experiment should provide, the maximum run duration, how long we would like this experiment to be allowed to run. Users can specify the database service level to enable parallelism. We'll choose the medium setting. There are various model metrics to choose from to affect the ranking of models. We're going to have balanced accuracy. And you can even select the algorithms for the experiment to consider among those in-database algorithms. With that, we're ready to start our experiment. We have the option to choose faster results or better accuracy. We'll go with faster results. This starts the experiment. In the progress bar, we start off with initialization, then determine which algorithms should be tried for this dataset, followed by adaptive sampling, feature selection, model tuning, and prediction impact. Here we see some of the algorithms that have been selected. Let's switch to another experiment that's already completed. Here are the settings used for this experiment. The plot shows the improvement in the model metric, in this case, balanced accuracy. We have our leaderboard of models, each with its corresponding accuracy metric. And there are additional metrics that we can add to the list as well. Opening the progress bar, we see everything was completed successfully, but if there were warnings or errors, they would show up here. By clicking on a model, we view model details, such as prediction impacts, which ranks the predictors that most impact model performance, and also a confusion matrix, which tells us the percentage of predictions it gets correct and what type of errors were made. Here we see about 75% of the predictions are correct. Other algorithms were tried as well, but the SVM Gaussian model performed best. If desired, users can generate a notebook for Python code, which will build the model using OML for Pi. And we see the notebook has been successfully created. Notice we renamed our top model to make it easier to recognize. This model can be used directly from the database, or we can deploy it to OML services, a lightweight model deployment component on Autonomous Database with REST API. I'll say more about that later. Let's deploy this model. The name is pre-populated. We'll specify the URI, The version will give it as 2.0, and the namespace will be demo. And we want to share this model with others. The model's been successfully deployed, so let's go to our model interface and filter the results to view this deployment. So here's the model we just deployed, and this is its previous version. Clicking on the model name, we see our model metadata in JSON format, the predictors, the output, and target values. Clicking the URI, we have the OpenAPI specification. So now let's look at the SQL and Python APIs on Autonomous Database through OML Notebooks. We'll click on Notebooks, and this will take us to our Notebooks listing page. The one we're interested in is called OML Demonstration. The notebook server is starting, and now loading the notebook. The first thing we're going to do is check our connection to the database and enable parallelism with the medium setting. We'll deselect low and high and save these settings. Let's view the data from our earlier experiment. So we'll select star from customers. Here we see the data, what we're trying to predict, the column purchased, and various demographic predictors. For supervised learning, we'll separate the data into training and test sets by creating a view using the sample clause in a SQL query. Here we're selecting about 60% of the records for training and the remainder for test. Next, let's build a random forest model using OML for SQL. After dropping any model that might exist by the same name, we'll use the create model to function, where we specify the model name, that is a classification problem. We want to use all the data from the customer train view. The settings list we specified up here to indicate that we want to use the random forest algorithm. The case ID is the customer ID column, and our target, what we want to predict, is the purchased column. So this is all it takes to build a model in the database. Now that we have it, this model is ready to use to make predictions. Let's dynamically predict the purchase probability for a single customer. Notice that we're using the prediction probability operator in the select statement and the purchase product model that we created above, along with the values right in the query operator. We run this and see the customer's probability of purchasing the product. Scoring customers dynamically in batch with prediction and probability is just as easy. Here we select the customer ID, invoke the prediction operator on our model, as well as the prediction probability using our customer test data. In the result, we see the customer ID, with some of the customers being predicted as purchasers where the value is 1, along with the corresponding probability. We also talked about seeing details of the model itself. In the case of a random forest model, this includes the relative importance of the predictors when making predictions, how much they contribute to the model's accuracy. We're accessing one of the model detail views, and this shows the ranking of the predictors, with age as the most important, followed by years residence and education rounding out the top 3. We can also dynamically select customers with a certain probability of purchasing using a SQL query. Here we're selecting customers that are more than 80% likely to purchase the product. We also talked about getting prediction details to understand why a given prediction was made, what factors most contributed to this prediction. And so for the first customer, we see that age, years residence, and education are the top 3 predictors with their corresponding values as weights contributing to this prediction. Using OML for Pi, it's also easy to build in-database models. After importing the OML module, we use OML sync to get a proxy object to the customers table. Then we'll produce our customer train and test data using overloaded functions such as split that operate on data frame proxy objects, keeping data in the database. Here we're doing a 60-40 split. From there, let's build the random forest model providing this data. We create an RF object and invoke fit. And here are the details from the model object itself. The settings that were used, computed settings, global statistics, attributes, and the importance ranking. We can also dynamically score customers with prediction and probability. Here we invoke on our model object the functions predict and predict proba on our test data. And we merge those in a single result, our predictions. All of the data remains in the database. So the result contains the customer ID, the prediction, and the probability of purchasing or not. AutoML for Pi also supports automated machine learning, where we can perform automated algorithm selection and see a ranked list of algorithms that were chosen for our data set. In this case, we see GLM with ridge regression enabled, followed by neural network and other algorithms. Automated feature selection is where we select which features are most predictive for the algorithm selected. Invoking reduce on our training data produces this subset of columns. We've reduced the total number from 10 to 7. And then automated model tuning, where we efficiently choose model settings to produce the model. We invoke tune, and we see that the best model produced was a generalized linear model, where we have the settings and the attributes that were used. The resulting model is an in-database model that's ready to be used from SQL or Python, or even deployed to AutoML services for access from REST endpoints. So we've seen there are multiple ways to produce and consume models using Oracle machine learning. But another approach with autonomous database involves AutoML services. This component makes it easy to manage and deploy machine learning models using a REST API, providing a common service for model deployment, update, versioning, and prediction. With the AutoML UI, one or more of the models produced can be deployed to AutoML services for immediate use by custom enterprise applications, including those based on Oracle Apex, through the use of REST endpoints. Those who prefer a more code-centric approach can use AutoML notebooks with SQL and Python directly, as we just saw. The resulting in-database models can be deployed to AutoML services as well, or used directly from the database by enterprise applications. Oracle Analytics Cloud is integrated with AutoML, so in-database models can be browsed, selected, and used in dashboards seamlessly. In other scenarios, users can produce models outside the database in external engines, for example, using Python in OCI Data Science or a local Python environment. These models can be built using third-party packages like scikit-learn and TensorFlow, and then exported in ONNX format. Using the REST interface, they can be imported to AutoML services. And as before, enterprise applications and dashboards can easily use these models to make predictions. We've just seen how data scientists and other data professionals can leverage Oracle machine learning. However, there is a broader audience for machine learning with application users. With machine learning in the database, many Oracle applications have exposed high value-add functionality for end users without the need for enterprises to build models and instrument applications themselves. For example, Oracle HCM can identify employees likely to leave, along with the top reasons, and explore what-if scenarios. Configure Price Quote can predict the likelihood that customers will purchase at current pricing levels, as well as the win probability to guide sales activities. Depot Repair can predict root cause and best fix for equipment, while allowing users to automatically apply accepted recommendations. Application development teams adopted Oracle machine learning due to the simplicity of being in the database, which results in ease of development, integration, and deployment. No-code user interfaces increases accessibility by citizen data scientists. And keeping data in the database increases security, scalability, and architectural simplicity. Still others cite the benefits of leveraging one version of truth from the data warehouse. So for more information, I'd like to call your attention to our blogs, located using the link provided here. One of our recent blog posts discusses the top 10 reasons to use machine learning in Oracle Database. For additional SQL, Python, R, and Notebook examples, check out our GitHub repository and see our library of office hours sessions. Sign up to get notifications of future events. Thank you for joining this session.